Hello and welcome to the Kinetics Big Idea 4 podcast on factors affecting rate. This is the first set of notes in the kinetics unit. And this is going to be a super important topic because it is going to address rate. So in the last unit, we talked a lot about whether things would happen in Big Idea 5, which actually they're a little bit out of order there, but whether a reaction will happen or not. Just because a reaction will happen does not necessarily mean that it will happen fast. Example is decomposition of certain types of rocks. It will take a really, really, really long time for that to occur, even though it has a negative delta G. And if we remember, a negative delta G means the reaction will occur at that particular temperature, but it doesn't mean that it will happen quickly. So kinetics is the other piece of that question. Will something react or won't it? And kinetics will tell us, well, if it does react, how quickly can we expect it to react? So let's take a look at the factors that affect the rate. Okay, before we can talk about the factors that affect the rate, we need to talk about the theory that guides all of kinetics, which is called collision theory. And this is one of those theories that the name kind of makes sense. In order for chemicals to react, they must physically collide. They must actually touch and hit one another. And this is really important because whenever we think about that, we think about chemical reactions. We put them in a beaker together and things are moving around and we can't really see what's happening because it's at such a small level. Microscopes can't see it. But we know that in order for chemicals to react, they have to collide. And they have to collide with enough energy. And in some reactions with larger molecules, they also have to hit with the correct orientation, or sometimes it's called alignment or geometry. So basically, if you have this really big molecule, and only the end is reacting. Let's think of an organic molecule. I'm thinking that just the end of the molecule is reacting. It has to hit there. It can't hit on the opposite end of the molecule. So that's what collision theory states. Chemicals have to react. They have to hit with enough energy. And this enough energy, by the way, this ties in with the piece of your activation energy, the energy of activation. They hit with enough energy to either break bonds or to make something happen to get this process started. And they have to align in the proper orientation. This is mostly with larger molecules, such as in biochemistry or organic chemistry. All right, so if we want to increase the speed or the rate of the reaction, well then, we need to do something to increase collisions. So our factors are going to talk about these four things. I can increase the number of collisions, so make the molecules go faster. I can increase their energy, right? So I can make them move faster so they hit harder and therefore increase the likelihood that there'll be a reaction. You can ensure proper alignment. This mostly has to do with biochemistry, with enzymes, working as catalysts to ensure that the proper location is highlighted. Or you can also change the pathway. So reactions don't happen in one step. They happen in a series of steps. Well, if I can make it happen in a different series of steps, it's easier to occur. That would also make the reaction go faster. So all of these things are going to factor into why our six main, there are more than six, but six main factors increase the speed of reactions. And that'll be on the next slide. Okay, so here are our first two of the six factors which affect the rate of a reaction. The first one we're going to spend a considerable amount of time talking on because it relates to something called rate law, which is kind of an interesting, so it's called rate law, which is kind of an interesting concept. So basically, if you increase the concentration means molarity of a solution, then you will increase the rate of the reaction. And this is basically due to the fact that if you think right over here, we have a little beaker diagram. So if I have a very dilute solution and I have chemical A, which I've got here in yellow, and chemical B that I'm going to put in green. Well, if they're really far apart, they're really dilute, then they're not going to collide with one another. And if they don't collide with one another, then that's not going to create a reaction. Well, if all of a sudden I increase those concentrations, so I'm making more of these green ones, now I'm increasing the likelihood that those chemicals, the yellow and the green, are going to collide and cause chemical reaction. just blanket increase in concentrations will not work for all chemicals. Well, first of all, obviously, they have to be dissolved into the solution. So they have to have a molarity. So solids and things like that, it wouldn't affect it because they don't have a molarity. But also some concentrations don't matter. And that has to do with something called mechanisms, the step-by-step at which the reaction happens. And we'll spend a considerable amount of time talking about that. But generally, we consider that if you increase concentration, you increase the speed of a reaction. And let me give a quick example of that. If you have 1 molar acid and you put zinc metal into it, you remember that creates hydrogen gas and generates heat. The reaction will happen, but it happens pretty slowly. Now, if you change that to 6 molar hydrochloric acid and you put the same piece of zinc metal in, it will happen. The reaction will happen lightning fast and generate a considerable amount of heat all at one time. And so that's a classic example of how if you increase concentration, you will increase the speed of the reaction. All right, the second factor that affects rate is catalyst. And we will spend a lot of time talking about catalysts when we talk about mechanisms. But just generally, catalysts always will lower the activation energy. So if we remember from an energy diagram, this would be our activation energy. So for what I have outlined here in green, that would be, and remember, we don't measure it from zero, we measure it from the reactants. We measure it from that line right there. So if you increase or if you have to add in this activation energy, then the reaction can occur the rest of the way. Well, what a catalyst will do is it will lower this activation energy and allow the reaction to happen much easier. So that's going to make the reaction go faster. The other way that a catalyst can do it, in addition to lowering the total activation energy, is to make the reaction happen in what's called a different reaction pathway. So where you have this first reaction here in green, so that would be your normal reaction without a catalyst right here. The one with the catalyst will occur, but it's going to happen instead in 2 steps. So it'll have an initial activation energy and then a secondary activation energy. And overall, this will be lower than the first one. And so in both of these, it lowers the activation energy. It's just the method by which it does it. Catalysts, if we also remember, if you've taken biology or if you haven't, you've probably heard of them, are also known as enzymes. And enzymes help to lower the activation energy by producing the proper orientation, the geometry to allow the chemicals to react. So that would go back to our collision theory again, that it makes sure that there's a specific opening for the reaction to occur in very large biological molecules. Okay, so we're going to move on to the next few factors that affect rate. All right, so here are our next 2 factors that affect the rate of the reaction. So we have pressure, which will affect gases only. So if you have an increase in pressure, you have an increase in the speed of the reaction. That should make sense because if you increase the pressure, the molecules are going to collide more frequently because everything should always come back to collision theory. So if particles are colliding more frequently, then you're increasing the probability that a reaction will occur that generally will speed up the reaction. Also, if you increase the pressure, they collide with more force. And if they're colliding with more force, that means that that is going to more likely produce a reaction. The next one is surface area, and so this is going to deal with solids. So solids don't deal with concentration, but they do have an impact on what's called surface area. Surface area is the amount of available space in order for chemicals to react. So it's the outside layer of that chemical. Well, if you pretend like you have a piece of metal here, and I know I've only drawn it in 2D here because it's a little hard to draw 3-dimensional. So let's just pretend 2-dimensional. So if I take this, let's say, piece of metal, let's say this is a piece of zinc, and we put this into hydrochloric acid, only the outermost part, so in 2 dimensions, the outermost part of this is available for reaction, meaning all of this on the inside, it can't react. So if I kind of scribble here in white, all of this is protected by that outer layer. So only that outer part in orange can react. And then once this reacts, then the underlayer can react, then the underlayer and the underlayer. But that's going to take time to eat away at that metal. Well, we take the same piece of metal and we divide it up into smaller pieces. Now you still have that outer area. So what I'm highlighting right now is the same space that you would have, same surface area you would have here, but you've now exposed new surface area. So I'm going to highlight that in green. So all of this is new surface area for the chemicals to touch. The chemicals cannot react. So let's say, for example, hydrochloric acid cannot react with any of the metal that's trapped on the inside, what's not on the surface. Because remember, in order for them to react, they must collide. They can't collide if they're protected by an outer layer. So in this one, you still do have inside parts that are protected, right? That's what I'm highlighting in white. But it's a lot less than what you have in here. You have a lot more available surface area. And the more surface area you have, the faster that reaction is going to go if you have a solid involved in your reaction. The fifth one, I'm going to draw that right down here. The fifth one is going to be an increase in temperature. And this definitely makes sense that if we increase temperature, we're going to increase the rate of a reaction. And that is because if the molecules are moving faster, they're going to collide more frequently. And also if they're moving faster, right, if they have, this means higher kinetic energy. If they have higher kinetic energy, that also means that they're going to collide with more force. And that means that they would have a more likely chance of reacting. So there's one last one, and I'm going to have to clear the slide to set that one up. All right, the last major factor that affects the rate of a reaction is some sort of physically mixing, which can be stirring, blending, shaking. And if you think this should also make sense according to collision theory. So let's say we have a piece of metal. I'm just sticking with the zinc and hydrochloric acids. We add a piece of zinc in down here to the hydrochloric acid. What will happen is the area right around here will react because that's where the acid is physically coming in and touching this piece of metal. Well, what's going to happen is the concentration of reactants in this area, if you're letting it stay still, this is going to drop and slow the reaction down. And you're also going to build up products just right in this area, right? Because there's no reason why it would move away from this area very fast. Diffusion happens very slowly in liquids. So everything's going to stay right in this area. Well, if I all of a sudden come in with a stir stick, okay, and I swish this all around, not the most graceful drawing, but by swishing this all around, I'm bringing in the higher concentration acid from up here that hasn't reacted yet, and I'm dispersing the product. It's kind of blocking this reaction from happening, and I'm dispersing it into the rest of the solution so you have more uniformity. So that will happen to increase the rate of your reaction in most cases. There are other factors besides these six, but these are the six main ones. These are the ones you're responsible for knowing. And it's true in almost every reaction that as a reaction goes, one of the biggest rate determining factors is, it's not exactly considered one, but you have to realize that time is a factor for consideration in all reactions, because as time goes on, concentrations will drop, and anytime you have a decrease in molarity, you have a decrease in rate. So most reactions will be the very fastest the moment that they begin, because of the concentration dropping. Now, sometimes temperature will increase, and that can actually increase the speed of that portion of the reaction. So it can be a little bit more complicated than that, but most reactions are the fastest when they initially first begin to react. That's not really a factor that affects it since we can't control time, but it is something to consider as you study the rates of reactions, is that they're not going to stay the same rate throughout the entire time because things are changing, like concentration or temperature or your building pressure or whatever's going on during the reaction. It doesn't stay static. So the next podcast is going to deal with how we actually calculate the rate of a reaction, and then how we calculate it over time. And we'll also go into what is a rate order, which is really important for the concentration of reactions. Thank you.